Okay, let's look at how to do a heat of solution problem. Okay, the first thing that you should notice about a heat of solution problem is that the units are in kilojoules per mole. So what we have to do a heat of solution problem, we have to figure out how many kilojoules, okay, that are absorbed or released, and divide that by the number of moles of the solute that we react. So the moles of solute. Okay, that's like the moles of the chemical that you put in there. Okay, so when we try to calculate kilojoules, okay, we're going to use the formula Q equals mc delta T. And when we do the moles, we're going to set up a picket fence, figure out the moles. Okay, so first, let's do the Q. So what we're going to do is we're going to figure out the heat that this thing either absorbs, the chemical either absorbs or releases when it's dissolved in water. Okay, so anyway, we're going to use Q equals mc delta T. The first thing is we're going to write the Q equals, now the M is important. It is the mass of the solution, which contains both the chemical, which is this 25.3 gram, and how much water, because those two added together will be the mass of the solution. So you can see that the mass would be 150 plus 25.3, which would give you 175.3 grams. Okay, that's a key thing that a lot of people forgot on the last test. Okay, then we're going to multiply that times the specific heat of our solution. And in this case, we're just going to use the specific heat of water, which is 4.18 joules per gram degrees Celsius. Okay, then we're going to multiply it by the temperature change, which is always final. So we're going to take 20.7 minus the initial, which is 25.8. Okay, and anyway, when we do all this math, we end up getting that our Q equals a negative 3,737.04 joules. But this Q right here is for the water, because we are actually, the water is what's increasing in temperature. So you got to think about if the water, well actually the water is losing heat. It's decreasing in temperature. The heat is leaving the water. So if you think about it, it works like this here. So here we have our solution, okay, and the temperature goes down because what happens is heat goes from the water into the chemicals. And so what really happens is at the end, okay, we have a net loss of heat from the water. Okay, so there's a net loss, okay? So anyway, so the thing to remember is that the Q for the water will be the opposite, or for this chemical will be the opposite from what it is for the water. And I wrote copper sulfate, it's supposed to be copper 2 nitrate. Okay, so the Q for the copper 2 nitrate is going to be the opposite of that. Okay, so remember that if the temperature cools down, your heat of solution should be positive for the chemical, or endothermic. If the water heats up, okay, then you're going to have the heat of solution should be negative. But in this case, since our water cooled down, it went from 25.8 to 20.7, our heat of solution should be positive for the chemical. Okay, now, if you notice that that is in joules, we need to get to kilojoules. So we're going to move the decimal 3 spots to the left. And so roughly we get about 3.7, we went one more spot, 3.74, not 3.4, 3.74 kilojoules. Okay, so there we have the kilojoules. Now we need to get the moles of the solute. So to get the moles of solute, we're going to take the 25.3 grams of copper 2 nitrate, so that's going to be Cu, that's 2 plus, nitrate is 1 minus, so it's going to be CuNO3 2. Okay, and we're going to change that to moles using a picket fence. And so we have 1 mole of copper 2 nitrate. And if you add up the molar mass of that, it's around 187.56 grams. And so the grams will cancel. And that ends up giving you, when you do the math, about 0.135 moles. So it's going to equal about 0.135 moles. Okay, now, so we have our kilojoules here, we have our moles here. So what do we need to do at the end? Well, we got to just take the kilojoules divided by the moles. So we're going to take 3.74 kilojoules, and we're going to divide that by the moles, which is 0.135, and then that ends up equaling 27.7 kilojoules per mole. Okay, that number is positive. Let's double check to make sure that makes sense. Okay, so we have a positive heat of solution. To have a positive heat of solution, that must mean it's endothermic. That must mean the chemicals absorb heat energy from the water. And so the water temperature did go down, so that must be accurate. Always double check it at the end. Okay, a lot of times when I do the problems, I don't really worry about the signs until the end, whether it's positive or negative. I just think, hey, if the temperature went down, that's endothermic, my sign should be positive. Or I'll say, hey, my temperature went up, therefore my heated solution should be negative. That's how I try to do it sometimes. Okay, that's it.